Hello guys and welcome back. So now we took a look at how we can convert a linear function into something a lot more interesting. But if we look at all these functions, they all have some kind of mirror on them. It's just a half basically that we're creating, and then the other half is just a mirror of that. And a lot of other equations have something like this where you don't see a mirror. It's not reversal, and it has an anchor point where it flips direction and starts going in a different behavior. And these are some of the examples. This is the one that I'm interested in showing you guys how to implement. And you can see it's starting this way at the beginning and then quickly changes into this. We can specify that anchor point, which is here, here, or here, and that will decide how this function behaves. And this may be a little bit more advanced, but I still think it's very, very doable, and I think all these functions are very easy to implement. They have an implementation for all this. It's actually much simpler to look at it this way, but I want to show you guys and explain how to read this and implement that version. So let's take a look. So this is the function we have. We have a linear value. Let's create a point fault. Same thing, using the UV coordinate. And I'm gonna do a vector to float. Let's take a look. It's our linear value. It goes from 0 to 1. Okay, and what the difference between the previous and these equations is that they have two parts. They have some kind of if statement. If x is less than a, which is a constant, use this part. If not, use this. So this sign here means less or equal. If x is less or equal than, let's say, 0.5, which would be here. Here you can see the r or the a, 0.5. Use this function, otherwise use this version. So let's implement the top one first. But we need this a constant. So let's create that. I'm going to set it to 0.5. Let's call this a. And then we're going to compute this. So this is our x. Let's create a null. And say, okay, this is our x. And first we need to compute the power of a. So power of by 2, exponent 2. And then we're going to compute the x minus a. So subtract x minus a. And then we're going to compute the power of this result. Let's call it x minus a. Very simple. We're going to compute the power of that, as you can see here. And then we're going to subtract a. We use x. And then we're going to subtract that from this, and then this symbol here means the square root, so we want to compute the square root of all of that. Let's do this. So that's the square root, and then what we want to do is we want to create this this statement, this if thing. So we're going to compare a. If it's less than if x is less than a, do this, otherwise do this. So we're going to use a compare node. We want to compare x with a, and the first we want to do less than or equal. You can see it here, and if that's true, we want to use a two-way switch node. So if this condition is true, we want to use this result, otherwise use the second version, which we're going to implement. So let's plug this result and see what we get. I'm going to use a set vector component, and change the y only. That's good. I'm going to take the p, and we're going to connect that to the position. And there we go. Let's change the height. Cool. So this is the first part. You can see it here. And now we need the second part. So let's do this. We need first 1. So let's copy that. Call this 1. We can't name them. Constant 1. Set it to 1. And then we need the 1 minus a, so let's do that 1 and subtract a. And then we're going to compute the power of that, so let's copy this. Power of 1 minus a, and then x minus a. So let's subtract x minus a. That's good. X first, okay. X minus a. Let's compute the power of that. And then this is x, this is 1 minus a. And let's compute the, subtract that 1 minus a from this. And then we're going to compute the square root of all this. And then we're going to take that 1 and subtract it from this. And this is our second input. And there we go. This is our function with a equal to 0.5. Let's change a. There we go. And we're getting this equation now. Okay, let's take it further. Let's copy this guy and use it with the maybe not this. Let's copy all of this. Let's copy this, and I want to use it with the circle to start with, and then go from there. So let's do that. And let's move this to the side. We don't need it. And I'm going to take the multiply, not that. And we'll add it here. So we need this result. Instead of changing the y position, we're going to compute the cross product of n, because we want to have it point outward. And then we're going to normalize it just to be sure. Previously we didn't do that, but that's fine. And then we're going to multiply this by this component. And then we're going to add all this to the position. Okay, let's take a look. There we go. And let's add a multiplier here to a global multiplier. And this will change the whole equation. Now, as you can see, we're changing. It's fine. Let's see how it looks like. I'm going to export this multiplier here. Okay. Yeah, this one is changing the 2 points, so it's a bit trickier because it's not looping. But I think you guys got the idea. And increase that, and then we have obviously a, which we can change, and we can also change these exponents, and that will also affect the result. But we probably would want them to be in sync, because it's like there is a mirror basically. So whatever we change the power of a, I think we need to change the power of all the other values so they are in sync. Let's see. Yeah, maybe something like that. Cool. So we can also change the range of x. So if you range between 0 and 1 to -1 and 1. So let's do this. Let's add a ramp, and I'm gonna make a mirror inside. Basically, change the range so it goes from 0 to 1, and then from 1 to 0, and that will make a mirror inside this. It's probably a bit complicated at this point. So let me change this here. Let's change this back to 1, and that's good. let's change the exponent back to 2, and I'm going to set this black. Okay. As you can see, now we're getting a mirror of this function. Now why this is happening? It's very, very easy, but I think it's worth explaining so you guys understand it better. So let's copy anything. And I'm going to take the x and plug it into the height, the y position. Okay. And I'm going to add a ramp instead. Okay. Right now it's going 0 to 1. We're not changing this range. Okay, it's the same. But if we take this point and move it to 0.5, and then take this black point and copy it and move it all the way to the end, we're going to make it change the curve, the ramp, so it's a mirror. Okay, it goes from 0 to 1 and 1 to 0. And this is basically the center of it. And that's what I did here. Okay, if I move this, you'll see it moves the ramp. And again, this is another very powerful way of doing shapes. We can obviously, let's see, let's create a multiply, or I'm gonna do this. If you hold Alt and click, we'll create a dot. I'm gonna create a parameter, and this way I can control it outside. I'm gonna call this A, and let's go up. And this is our A value, and that's the center where it switches. Okay, we can use the multiplier as well to change this whole thing. We can use this, probably do something like this as well. It's never enough. There's so much control with just the simple version. Okay, let me I haven't done this before, so bear with me if I fail. Now, a lot of you guys may be wondering what's Vex then, where all this scripting if we can do everything here. Well, as you can see, it gets pretty overwhelming with nodes quickly, and this equation here is actually very, very simple. And I'm going to show the Vex version. I'm going to try and implement it. I don't know if it's going to work. If we fail to implement it, we'll do it in the next video. Okay, let's start. We need a constant a, so let's create a float called a. Let's set it to ch. Call this a control. If we do this, the ch thing, and give it a name, hit the plus sign, it will create a slider for us. And now we're dynamically changing this value. Okay, we want the exponent of this, so we're going to use a power function, pow, that would be it. So let's call it float a2. It's equal to the power of a2. That's the syntax. And then float x minus a. So I'm just creating each part by itself. It's equal x minus a. Now it's going to give me an error. What is x? Well, we can create x. Float x is equal uv.x. That's what the x information is. Okay, we're just making a copy here. So x minus a, and then we're going to compute the power of that. And then we're going to compute the square root of that. So let's call this float part 1. And then we're going to compute the square root. This is the function of a2 minus this. obviously nothing changed because we're not changing any value. And then we're going to do the second part, and then we'll show how to do the if statement. So the second part is going to be the square root. We need float 1 minus a, and I will do 1 minus a. Get the power of that. And then we need x minus a, and also we're going to compute the power of that. X minus a. Okay. And then we're going to compute the square root of that, and minus 1 minus the square root of that. So let's call this part 2. Let's go 1 minus square root of, let's call this minus. I think we have it here. It's the same part, so we'll use x minus a. It's the same thing. I'm not gonna redo it. Okay, so it's 1 minus a, and then x minus a. So this part here, and then this guy, and then 1 minus the square root. Now we're gonna do the if x is less or equal than a, we want to change the y position, v dot p dot y is equal part 1, else if that's not true, part 2. And let's see, I'm gonna add semicolon here. What else? 1 minus a. I think we cannot start with a digit there. Okay. Oh, sorry. Yeah, it's minus. Yep. Cool. So let's see. A is working perfectly. And we can also fit range. We're changing the height. Oh yeah, it's not going to work on this. So let's try it with just a line, because we need to change the offset. And let's connect this. Cool. So it's working here. Perfect. And then in order for it to work, we need to change multiply it by the normal and then offset p. So let's do this. We're going to do this. The result, let's call it vector result, is equal v at n multiplied by part 1, and then we're going to change p. V at p is equal v at p plus n. So that's how we offset it. We're adding the two vectors together. And then I'm going to do the same thing. I can save a line here, but it's okay. Result. And here, same thing. Going to multiply v by n. Okay, and then we also need to compute the cross product of that. So let's do that separately before we mess it up. So let's do another wrangle just to be safe. V at n is equal cross of v at n with 0, 1, 0. And there we go. it's working. Now the last part is we want to fit range this using a ramp, and it's a bit tricky with this UI to do the ramp, so we'll just do it using something like this. And I'm going to copy this part here. I'm going to create a point vault, and it's much easier this way. So we're going to take the Y position, and then we're going to bind export that as UV. So we're changing the UV coordinate with this ramp. That should do it. Okay. There we go. That's our Vex version. And you can see it's much easier to change, I think. But the same result, you're not going to see any difference, to be honest. It's just this looks like this, and this looks like this. And again, this is basically all a bonus if you want to take it further, or if you're curious as to how math and Vex and all this stuff is working inside of Houdini. This is a good way to look at it. Okay, let me change this. I want to see it how it looks. Cool. Yeah, very, very interesting. Cool stuff. Thank you guys for watching, and see you in a bit.